Okay, good afternoon. So this will be our last tutorial, and this Friday will be our last lecture. And from this Friday, I'm going to cover diffusion models. Basically, just an introduction of diffusion models, and it won't be included in the exam. Okay. Since this is the last tutorial, I will be a nice guy. Yeah, we take attendance now. Okay. Okay, done? Yeah, I will show this once again before I enter the class. All right. I've posted the Q&A for last week's lecture online. So you can find the Q&A PDF on NTU Learn. Okay. So if we have some time there, we can go through some of them. I removed some questions, too easy or not relevant. So these are selected questions and answers. And before I start the class, I have a request. This is not part of the course, it's purely voluntary. So I just wish to request you to participate in a user study in my experiments. So my lab is working on diffusion model. So we use diffusion model to generate images. We are doing a user study to see how good the generated images are. Okay, so there will be 20 questions, and it's expected that you can finish that in just 5 minutes. It's preferable if you can do it on your laptop so that you can look at the images more carefully. So the interface is something like this. Is on Google Form. I have already posted the link on NTU Learn. Yeah, if you click the link under the first announcement, it will lead you to the form. Okay, then you can start your user study. Yeah, please help me to complete this. If you have time, just spare 5 minutes to do the survey. Yeah, thank you for that. And okay, let's start the tutorial. If you remember what we ended last week, we basically mentioned that we will cover this model in the tutorial. This is DC gun, okay, that uses convolutional layers in the generator, yeah, as well as the discriminator for generating images. Okay, so this is the structure of the generator. Yeah, I didn't draw the structure of the discriminator. So this is the generator. And as you can see, what we are doing here is that we are going to project a random vector of 100 dimension, okay, gradually to a 3-dimensional output with 64 times 64 spatial dimension. Okay, that will be our image generator. And within network, we are going to study the so-called deconvolution. Another name of this layer is called fractionally strided, or another name is called transpose convolution. Okay, transpose convolution. So we are going to use this special layer to upscale the features step by step until we reach the desired dimension, right, or desired resolution. So let's start from the beginning. All right. This is an introduction of DC-GAN. In a nutshell, what we are doing here is that we are going to train a discriminator that make up of strided convolution, or the so-called transpose convolution, Bashnov layers, and leaky Renew. Okay, I'm not sure whether you know leaky Renew. I believe you might have heard this before. For Renew function, for Renew function, you have your activation being 0 at the negative regime and being a linear function at the positive regime. Okay, that's Renew. For leaky Renew, so what you have is a linear function at the positive regime and a slight slope, okay, at the negative regime. This is called leaky Renew. And this part, is the main difference compared to Renew. So Renew has the problem of having so-called dead neurons. It would lead to dead neurons occasionally. Okay, which means the neurons, they don't update anymore. It cannot learn anything anymore when it enters this negative region because it's 0 activation, so no more gradients can flow through the neurons. That's why if you use this, then you've got a risk of having dead neurons. And the reason of having a small loop over here is that we allow some small amount of gradient to flow through your neurons, so that you no longer have the dead neurons problem. Okay, so this is leaky Renew. And if you back to the slide, to the code over here, so that's the discriminator. And for discriminator, we would expect having an input of 3 times 64 times 64 input image. 3 because we have RGB channels, 64 times 64 because that's the resolution of the input image. And for generator, okay, we are going to use the transpose layers, and we are going to use the Bashnov layers and Renew activation function. Okay, so let's start. So we import the libraries, and we use Torch Vision, because we are going to use the data set called Celebrity A. And then we define the root directory to store our data, the batch size being 128. Okay, this is the image resolution, 64 times 64. Number of channels because we have RGB. And the latent vector that we feed into the generator is 100 dimension. And that's the feature maps in generator and discriminator. That's some hyperparameters over here. We use the same learning rates for our generator and discriminator. And that's the hyperparameter for our random optimizer. Okay? So we are going to use a very popular data set called Celebrity A phases data. Okay, it basically consists of a lot of images collected from the internet that feature different celebrities. Okay, with attribute label. So we are not going to use the attribute label. We are only using the images to train our model. So you can download from the dataset site, okay, or you can just get it from Torch Vision. So this is what we're doing here. So we call for Torch Vision and load the celebrity A data and store in our root folder, okay? And we are doing some transformation to the data. Okay, basically we try to resize it because the original data set has different resolution. Okay, all images have different resolutions. We resize it to a common size of 64 times 64. Then we do a center clock and then normalize it on all the 3 channels. And that's it. Okay, we load the data using data loader. That's where we define the batch size and whether we want to shuffle the data randomly. And then we try to show some training images we have. We show 8 by 8, so that's 64 images over here. So here we basically show a selected set of images of celebrity. You can see that it's very different in terms of the resolution, kind of in gender, with different attributes, and also with different colors. So it's a pretty challenging data set to learn. Okay, now we are ready to define our network. First, we define a function to initialize the weight. Okay, there are many ways to do that, and in the DCGAN paper, what we are doing is that we initialize the weight with mean equal to 0, and we have a standard deviation of 0.02. All right, and this is user defined. So this is the weight initialization function. All right, and then you can see that we also initialize the batch norm as well. Okay, the batch norm layers as well. Okay, this is the design of the generator. Okay, so the input is 100, a random vector with 100 dimensions, and the output is 3 times 64 times 64. That's the size of the image. Okay, and you can see that we accomplish this mapping through a series of so-called deconvolution layers, or we call it transpose convolution layers. And each of them will be paired with 2-dimensional batch norm layers and radial activation function. Okay? And at the end of the network over here, we will use a tank function. And remember that the tank function will give us the range between -1 and 1. Okay, that's the tank function. We put it at the end of the generator because that's the range we want. Okay, and okay, this is the diagram, and if we want to turn it into our class definition, that's what we have. So you can see that there are multiple COF transpose 2D followed by batch norm 2D and radial over here. Yeah. So we have a series of these combination until we reach to the final layer that ends with a tank function over here. Okay, it will be easier later when we print out the architecture, then you will see how these numbers turn into the actual kind of design of our model. So if you check this Conv transpose 2D, I will just copy and paste over here. Yeah, you can search it on PyTorch documentation. Okay, that's the arguments that you have to provide, the number of input channels, the number of output channels, the kernel size, the stride, yeah, so on and so forth. Somehow it's like a convolution function. And okay, so yeah, you can see here the layer is also known as fractionally strided convolution or deconvolution. But this is not a popular name, yeah, because deconvolution actually carries a different meaning. Okay, it means inverse of convolution. We are not doing deconvolution, so we usually will use this name. Okay, it's a 2D transpose convolution operator. Okay, and now we are going to use this in our architecture. Basically, what it does is that it will increase the spatial resolution. Yeah, we increase the spatial resolution. So let's create the generator. Then we initialize the weight, and we print out the model. Okay, you can do print net, and that will give you the network architecture with the hyperparameters. Now you can see that the input dimension here originally is 100. Okay, it's 100. Then that would give the output is 512. Okay, then the next layer will receive a 512 channels and produce 256. So kind of slowly reducing the number of channels, and eventually we reach the output channel being 3, okay, which is the RGB channel that we want. All right, and here it uses a very special kernel size in DC Gun. Use instead of 3x3, use 4x4 kernel. Yeah, it uses a 4x4 kernel, so it's kind of a very special design, and followed by the template. Yeah, that's the generator design. All right. Okay, then that's the generator, and now the discriminator will be much easier. Okay, it will take an input of 3x64 times 64 as input, and then process with a series of convolutional 2D, batch norm 2D, and leaky granule, and finally followed by a sigmoid activation function. Yeah, we use a sigmoid over here because we want to get the probability, isn't it? We should hope the output being in the range of 0 to 1. Yeah, that's why we use a sigmoid over here. All right, and all right. So you can see that we are using Conv leaky, Conv Bechdel leaky, Conv Bechdel leaky in a series, okay, in our network. And finally, we end with sigmoid activation function. And if you print out the model, so this is what you get. Okay, you take 3 channels as your input, and then slowly you increase the number of channels. Okay, number of channels to 512, and eventually you fit it into your sigmoid function. All right, and again here it uses 4x4 kernel. Yeah, that's special design in DCGAN. Okay, so for our discriminator, if you recall, is performing a binary task, isn't it? So it wants to, it needs to distinguish between real and fake input. That's why we are using binary clause entropy loss. Yeah, that looks like this. Okay, that's the binary cross entropy loss. So in the okay, so here you define the CE loss, and then you define the label that you need during training. Then you can start optimizing. Then you can define your optimizer. Okay, the training of DCGAN is more or less the same as the examples that we have covered in the main lecture, but there are some slight difference, okay, in terms of the loss function of the generator. So remember the generator is trying to minimizing this term. Yeah, if you go back to the lecture notes, the generator is trying to minimize this loss, okay, these values. But then in practice, what researchers found is that this loss function, it doesn't provide enough gradients or doesn't provide sufficient gradients to update the generator, especially at the start of the training. Okay, so they propose an alternative way to do the training of generator. Instead of minimizing this term, yeah, we will maximize this term instead. Okay, we're going to maximize this term instead. Okay, both would work, but this would work better. Okay, and that's the difference you will see when you compare the examples I provided in the lecture and the one we are looking at in this tutorial. And I won't really go through the detail of every single line. It's all documented over here. So if you're really interested in coding GAN, then you should have a look and understand the code. Okay, so eventually we can start our training and we'll print out all the loss. That will take some time because we're dealing with images. And if you plot the loss curve of the generator and discriminator, yeah, it looks something like this. It's a good sign that the loss curve, kind of the loss converges to a stable value. And what is more interesting is that we can use this function animation, the artist animation, to kind of put our result into a GIF. Yeah, let me reduce the size. Okay, so after training, yeah, we should get a series of these plots, and we can check the evolution of the generated images. Okay, so you can see that our images, after every 1,000 iterations, it gets kind of better and better. It starts from noise, then you get the shape of the structure of humans, then slowly we get better and better details in feature components. Okay, that's what you get, and Then you can plot the real images and fake images side by side, compare the red curve compared to the results, yeah, with the ground truth. So it's a very kind of straightforward tutorial for GAN, and you can have a look at it, yeah, and try to run it. So you might face a potential problem when you are trying to load the data over here. Yeah, it might give you a warning message saying that the data is too popular, so the server can't support all the downloading requests. So you have to wait for, I don't know, 24 hours to resume the downloading. Okay? Or if you want to get the images like instantly, then you should just download the data from the internet, and then you prepare the folder images by yourself. All right, so that's the tutorial. Okay, any question on this? Any question? Yeah, you can post a question here, or you can raise your hand and voice out. All right? Okay, I'll wait for okay, is leaky gradient typical for discriminator? Is design choice? Okay, you can use leaky gradient in generator as well. And leaky gradient is getting more popular compared to gradient because, yeah, as I mentioned, it won't avoid the problem of dead neurons. So you can use this leaky gradient everywhere. Yeah. Dead neurons the same as vanishing gradients. It's related, okay? Vanishing gradients means that you do not get a good gradients, or gradients becoming too small to update the layers, okay? Especially those layers at the bottom. Yeah. For dead neurons, it's not, the network is not experiencing vanishing gradients overall, but just specific neurons, the selected set of neurons, they are dead. Okay, they cannot be updated anymore. Not the whole layer. Yeah, it's more kind of a local issue. Yeah, attendance, I will show the attendance picture later. Okay, don't worry about that. Why does the generator output get fed into the tank function? Why it must be -1 to 1? It is a common practice to scale your images within the range of -1 to 1. Okay, when you prepare your data set, yeah, you need to do that, yeah, instead of from 0 to 255, which is the intensity level of each channel. Yeah, you make everything fall into the range of -1 to 1. And that would make your training easier, okay, and convergence would be better. All right? Yeah, I'll talk about the finals exam this Friday, okay? We'll talk about it in this tutorial. Yeah, please ask questions related to the tutorial or lecture. Yeah, may I know why are the normalization parameters to be 0.5? Yeah, that is kind of to make the images fall into the range of -1 and 1. So it depends how the data set was prepared in Torch Vision. So you can use these parameters to make it within the range that you want. Are there any disadvantage of leaky granule? There isn't a kind of a comprehensive comparison to say that leaky granule is bad at certain things, but there are some alternative activation function, okay? This is granule. There are other functions that provide more flexible, for example, the one I draw with Dutch curve. Yeah, instead of having a linear loop, we are having a curve, at the negative region. That kind of allows some non-linearity to the activation function at the negative region. So there's no obvious kind of weaknesses when it comes to leaky granule. Is normalization always needed? What if the data already falls between -1 and 1? If the data already falls between -1 and 1, then you don't need normalization. So we need normalization when the data has a large range, from 0 to 255 or from 0 to 1000. Okay, so typically you need to do some tests, some experiments to check whether normalization helps. It helps usually, okay? So we usually do normalization. Okay, and that's for the tutorial. And maybe also it's good to revisit some of the questions that you asked during the lecture. Okay, I remember, one of you asked, does the noise need to be calibrated or designed to be the exact same dimension as the real image? As what we have seen just now in DC gun, it doesn't have to do that. We don't have to do that. The input dimension is 100, but output is much larger, 3 times 64 times 64. Okay, so this is related to the design of the latent. It's usually like 100 or like 256 dimension. Okay, we don't want to make it overly huge. Now, because the goal is to compress your knowledge, compress everything into a low dimensional space. The latent should be low dimensional. That's why we don't need a high dimensional space. And that also related to another question on this. That is related where we discussed about the interpolation of latent. Remember, we have, let me open the slide. Remember we talked about this, okay? So we can actually generate a new latent by performing a linear interpolation between two different latents by using a coefficient m over here. Then you can use this Z-neo as an input to your generator to generate an image, and you will achieve a smooth transition between these two latents. Yeah, this is only possible when your GAN is trained well. Okay, if your GAN doesn't learn well, yeah, it will not give you a smooth transition because you do not have a good manifold. Okay, so if we draw it or kind of visualize it, okay, and again, you will feed your random vector to your generator, and you're going to generate a fake image, a fake image here. So you can imagine that once you have trained your generator, yeah, when the model converge, this you will learn a so-called manifold of your latent, okay, of your latent Z. So for example, your latent Z1 would be here, and your latent Z2 would be here. So when you perform linear interpolation between Z1 and Z2, you actually traverse in this very complicated manifold. Okay, say for example you have a Z new over here as a result of performing interpolation between Z1 and Z2, and if you fit this Z new to your generator, then you will get a fake image that kind of sits between sorry. Don't know why everything kept missing. Basically, you get a new image that sits between the images generated by using your latent 1 and latent 2. Okay, so that is because your GAN learns a smooth manifold that allows you to do this kind of interpolation, and thanks to the GAN's capability that allows you to generate an image from the latent. Okay, usually we will use this technique to check your GAN whether it learns something. Okay, because if it doesn't learn well, you cannot do this. All right, that's about the interpolation. And yes, if two students ask me whether is conditional GAN considered supervised. I remember conditional GAN, you provide class labels to control the generation. So it involves some supervised learning, some form of supervised learning, yeah, because it exploits the label data. So it's considered a supervised learning, okay, method. Okay, then is mood collapse somewhat similar or akin to underfitting? No, okay? Mood collapse is not underfitting. So underfitting means that our model is too small to learn to capture the data. That's why it's called underfitting. You get bad performance in training and testing. But mood collapse, it only happens to the generator when it it generates good images, but in a particular mood and not covering all other moods. It's called mood collapse. So mood collapse is not identical to underfitting. All right. And for other questions, okay, you can have a look myself. So, okay, we still have a little bit of time. If you do not have more questions, I would like to cover a little bit of something not included in exam. Okay, this is an important technique. Just that I don't have time to cover in this course, but doesn't mean that it's not important. So it's good to know. Okay, so I will show some slides to get you to it. And yeah, remember at the beginning of this GAN lecture, I show you you can use GAN for image to image translation. Okay, this is how I'm going to tell you how you can do that. The method is called Pix2Pix. It was published 7 years ago by Berkeley. Okay, by Berkeley. And as you can see, yeah, basically image translation means that we can feed in a modality and we can get another modality as our output. For example, we can get RGB from edge, we can get color image from black and white input. Yeah, we can play with this Microsoft Arrow. Okay, let's come back. Okay, so you can play with this demo online. Okay, you just need to find Pix2Pix, then we get something like this. Okay, so it's a very interesting demo. Okay, you just input the edge, and then you get a kind of near realistic possible image like this. Okay, so this is our GAN, the conventional GAN. Yeah, this is the value function. Yeah, we feed a random vector to our generator. We get a fake image, then the discriminator will decide whether it is real or fake, isn't it? Yeah, for example, we can actually change the random vector to an edge image. Okay. Yeah, we replace the random vector with an edge image, feed into the generator. Then we can get a RGB image. Then the discriminator will decide whether it's real or fake. Okay, this is kind of a naive, kind of straightforward way that we will redesign our GAN. Yeah, if you want to achieve image to image translation. But you will find that this method, it doesn't work. And it doesn't work because as long as the generator kind of generate a plausible bag that doesn't look alike to the edge, the discriminator will still give a real prediction, isn't it? Yeah, I can generate an entirely different bag here that looks different to this input, and the discriminator will still predict it as real. Because the discriminator doesn't have any reference. Now, for example, if I have this as our input to the generator, it produces this. Discriminator will not be able to tell whether this doesn't match with the input. Yeah, that's the problem of this kind of direct implementation. So what Pix2Pix tries to do is that instead of having the discriminator just looking at the RGB image produced by the generator, it also needs to have knowledge about the original or the initial input to the generator. Yeah. What you could do is that you can concat the generated image together with the input edge image together and feed into your discriminator. Then you train the discriminator to decide whether it's real or fake pair. Yeah? So with this reformulation, then you can train image-to-image translation with pix-to-pix. And this is very much aligned to the conditional GAN that you have learned in the main lecture. This time the condition is provided to the discriminator. Okay, in this channel. Okay, this is the condition to the discriminator. So the value function can be redesigned, okay, to include the condition as well. Instead of having just the image, and now you also have the input here, okay, to form the fixed pair together with the GX. Okay, while for the discriminator term, you have the X and Y, X being the real image and Y being the X being the edge, the real edge, and Y being the real image. All right, so that's the reformulation of the GAN. And with this setting, you actually assume availability of pair images of X and Y. For example, you have X being your edge images and Y being your real images as your training source. So you can easily get the X for free from your real image. For example, you can use Kenny edge detector to get the edge map for all your real images. And then you can use them to serve as your training source. So that's some results provided by pix-to-pix, okay? All right. And yeah, you can see how to turn a map into a satellite photo. And we can do many more applications like converting black and white photos to color images. Okay, so this Friday we are going to talk about diffusion model, and we are going to look at more advanced techniques of achieving this kind of image-to-image translation using diffusion model. Okay, Friday is involved more mathematics, but you will also see some interesting demos as well. So if you have finished your group project, then come to the lecture. Okay? A reminder to submit your group project this Friday. All right, if you have questions,